Hello guys, welcome on Tesla Adventures. In this video, we are going to discuss the pressure variations in an accelerated fluid. Now I know that you must be thinking that this is the hydrostatic part and why we are discussing the accelerated fluid. Now hydrostatic means that fluid is not flowing. Okay, so this is not flowing fluid. In fact, this complete system along with the container is accelerated in the upward direction. So I'll be assuming a observer inside the fluid. It is standing inside the fluid, and in the frame of reference of that observer I'll be writing down all the equations. So obviously in the frame of this observer this fluid is not moving, as well as if you consider the ground observer, then this fluid is only accelerated along with the container. It is not flowing. So in hydrodynamics we deal with the fluids which are flowing. So we can consider this case in the hydrostatics only. So let us assume that there is an observer who is standing inside this liquid, and along with the container it is moving with an acceleration of a in the upward direction. So you can now again imagine an imaginary cylinder whose length is dy and whose area is a. I have assumed that the area of cross section of this imaginary cylinder is a. Okay, so I have assumed this cylinder which is made up of this liquid only. And now obviously as this observer is accelerated in the upward direction, therefore a pseudo force would be acting on the cylinder along with the mg in the downward direction. So the total force acting in the downward direction would be mg plus ma, where m is the mass of this cylinder, and this force will be counterbalanced by the pressure difference. So you can see that the force generated due to the pressure difference would be acting in the upward direction. So the pressure at the bottom of the cylinder will be greater than the pressure at the top. Okay, so we can say that P2 minus P1 into area will be equal to mg plus a. Now this g plus a can be considered as g effective acceleration, and this P2 minus P1 is dp into area will be equal to m. Now mass of this cylinder will be volume into density, and volume will be dy into area into rho. This is mass, and into g plus a. So again cancelling a with a, dp by dy will be equal to rho into g plus a, and we can say that it is g effective. So dp will be equal to rho into g effective, and this dp by dy. So we can say that the pressure gradient, this is the pressure gradient. Okay, so this kindly excuse me because kindly forgive me because this writing is bad due to some technical error on the screen, so kindly ignore. I hope you are getting the things which I am writing, although my writing is already bad, but now at this time this is some technical error which is going on the screen, so just ignore it. So this is the pressure gradient, which is rho into g effective. So we can say that now the pressure will be increasing at a greater rate as we are going in the depth of the cylinder. So we can say that if this point, let's suppose if this point is A, let us see that if this point is A and if this point is B, so I can write down that pressure at B will be equal to pressure at A plus rho into g effective into this distance dy. So Pb will be equal to Pa plus rho, g effective is g plus A into dy. Actually the g effective is the net force F net in the frame of liquid divided by m. So the net force is mg plus ma divided by m. So this is g plus a. Okay, now if the container is moving in the downward direction, and obviously G is less than, in fact, G is greater than A is less than G. Because if the acceleration of container will be greater than the acceleration due to gravity, then this liquid will not be inside the container, and in fact the liquid will be in free falling state. And you know that free falling state is like gravitational free space, and in that space Pascal's law says that at the pressure at each point inside the liquid will be equal. So we are not considering that case, we are considering when A is less than G. So when A is less than G and acceleration is in the downward direction, then we can say that pseudo force will be acting in the upward direction and mg will be acting in the downward direction. So the net force will be in the downward direction because mg is greater than ma. So F net in this case will be equal to mg minus ma. Okay, and the G effective in this case will be equal to G minus A. So we can say that dP by dy, dP upon dy will be equal to rho G effective, which is G minus A. And hence if we compare 2 points, this A and B, then we can say that pressure at B will be equal to pressure at A plus rho G into H. Now this G will be G effective and G effective will be G minus A into H. So this will be the pressure variation. And this is the equipressure line. Actually equipressure line is just like equipotential surfaces. And as the name suggests, equipressure lines has only those points which are having equal pressure. So each point on this line will have equal pressure, and the orientation of equipressure line is parallel to the free surface of the liquid, because obviously free surface is also a equipressure line. So you should always remember that in the case of accelerated liquids, the orientation of equipressure line will be same or will be parallel to the free surface of the liquid. Okay, now let us take this another case, third case, in which this container is accelerated in the forward direction. So if the container is accelerated in the forward direction, then the liquid will align itself in such a way such that the back part of the liquid will be lifted up. You can imagine this thing, okay? And obviously if we draw the height, then this height will be equal to this height, which means that if the initial level of the liquid was this, then the height by which this front surface will go down will be equal to the height by which this back point will go up. Okay, we can say that. Now if we consider that why this happens, we can say that the mg will be acting in the downward direction and ma will be acting like that. And we know this is ma, pseudo force. And we know that the net force will be acting like that. And the net force will be m under root of g square plus a square. And we know that when we have studied the definition of fluid in the first lecture, we discussed that fluids are those materials which do not resist the tangential force. So if any tangential force is applied on the fluids, then they will begin to flow. But this fluid is contained in a container and it cannot flow. So we can say that there should be no tangential force acting on this fluid. And in order that there should be no tangential force acting on the fluid, we can say that the fluid free surface will align itself in such a way such that the net force becomes perpendicular to the free surface of the fluid. So this net force is perpendicular to the free surface of the fluid, and hence there is no component of net force which is tangential to this free surface. So we can say that this elevation occurs due to this phenomena. And now if we discuss the value of angle, then we can say that if this is theta, this is 90 minus theta, then this is also theta. So tan theta in this case will be equal to this upon this. So this is MA. You can see that this is MA. So MA by mg. So theta will be equal to tan inverse A by G. So this is the angle by which the free surface of liquid will align itself, and obviously each equipressure line will be parallel to the free surface. In the later part of this video, we'll be discussing the free equipressure lines also. So let us now discuss the same thing. Let us now find out the value of theta by different method. So we know that we have derived the pressure gradient by using that imaginary cylinder which is made up of the fluid only. And now to derive this value of theta, we are again imagining this imaginary cylinder which is in the horizontal orientation. So we have assumed that the length of this cylinder is dx, and the area of cross section of the cylinder is A, and the pressure at this end of the cylinder is P1, and the pressure at this end of the cylinder is P2. Now as we can say that the height of free surface of the liquid above this end is greater as compared to the height of free surface of the liquid above this end. So we can say that this H1 will be greater than this H2, and hence we can say that P1 will be greater than P2, because P1 will be equal to P0 plus H1 rho g, and P2 will be equal to P0 plus H2 rho g. Okay, now we can say that due to the acceleration in the forward direction, there will be a pseudo force which is acting in the backward direction, ma, like that, because container is accelerated in the forward direction. So to balance this pseudo force, because this cylinder is in equilibrium, so to balance, this is not an external cylinder, this is an imaginary cylinder which is made up of the liquid only. So it is not moving inside the liquid. In the frame of liquid, obviously we are standing inside the liquid. So according to us, the cylinder is at rest. So to balance this ma, the pressure at this side P1 would be greater than the pressure at this side P2, so that a net force due to pressure is developed in the forward direction. And that net force will be equal to P1 minus P2 into area of the cylinder, and it would be balancing ma. Now P1 minus P2 is, P1 is this one, you can see, and P2 is this. So P1 minus P2 is H1 minus H2 into rho GA will be equal to M. And the M will be volume into density. Volume is A dx, density is rho, and A is the acceleration. So cancelling A with A, rho with rho, we can say that H1 minus H2 upon dx is equal to A by G. And you can see that in this triangle, you can imagine this triangle, this is the triangle. In this triangle, this angle is also theta. So theta will be H1 minus H2 upon dx. Okay, you can imagine this cylinder. I'll write it down here. This is the so this complete this H2 minus H1 will be this one. This is H2 minus H1, and this is dx, and this is theta. So tan theta from this triangle will be equal to H2 minus H1 upon dx. So it is H2 minus H1 upon dx, and hence we can say that tan theta will be equal to A by G in this case. Okay, so this is the value of tan theta. So we have already derived this value and by the first method, and we have also derived this by this second method. Now let us move further and let us analyze the equipressure lines. Now let us see that this is the equipressure lines, and this is the liquid which is accelerated in the forward direction. So on this equipressure line there are 2 points A and C, and this is B, which is on another equipressure lines. So we can say that the pressure at A will be equal to the pressure at C. okay, because they are lying on a same equipressure line. And this point B will have some different pressure. So we will be writing down the pressure of B by point A, D and C. So we also know that the pressure at D will be also equal to the pressure at A and pressure at C, because they all are lying on a same equipressure line. So we know that the net force acting in this case will be equal to m under root of G square plus A square. So we can say that the G effective will be equal to F by m, and it would be under root of G square plus A square. This will be the value of G effective. So now let us write down the value of pressure at B by A. So we can write that pressure at B will be equal to pressure at A plus H rho G. Now you should always remember that while you are coming from A to B, you are moving only in vertical direction. And in vertical direction, the only force acting is mg. And in horizontal direction, the force acting is ma. And in this direction, the force acting is F net, the resultant of these two. So when we are writing the pressure of B by moving vertically downwards from A to B, then we have to consider the height, vertical height h, and we have to consider the vertical acceleration g only. So we can write down that pressure at B will be equal to pressure at A plus h rho g. This is the first equation. Okay, and again if we write down the pressure at B by D, so we can write down that pressure at B will be equal to pressure at D plus now let us consider that this length is L and this is G effective. So we can write down L rho into G effective will be under root of G square plus A square. And we know that obviously pressure at B should be same by these two formulas. Now first of all we can write down pressure at D as equal to pressure at A. So let us write down PB is equal to PD is PA and L rho under root of G square plus A square. Now you should just see that this in this triangle, this is hypotenuse and h cos theta is L. You can see that h cos theta is L, so L is equal to h cos theta, and hence h is equal to L sec theta, or we can just substitute the value of L as h cos theta. So PB will be equal to PA plus L is h cos theta into rho under root of G square plus A square. Now we know that tan theta is A by G, which we have already derived. So cos theta will be equal to G under root of A square plus G square. Okay, so let us substitute this value in this equation. So PB will be PA plus H cos theta is G under root of A square plus G square into rho under root of A square plus G square. Cancelling this. So PB will be equal to PA plus H rho G, which we have already written by moving from A to B. Now let us move from C to B. So we can say that as the container is moving in the forward direction, so in the frame of the liquid, a pseudo force will be acting on the liquid in the backward direction, which is Ma. So pressure at B will be greater than pressure at C. So we can write down that pressure at B will be equal to pressure at C plus x, which is the distance between C and B, and rho into acceleration should be A, because the acceleration in x-axis is A. So we can say that it would be x rho A. Now again you know that PC is equal to PA. So I will be writing PB is equal to PA plus x rho A, and we can say that in this triangle you can see that, or in this triangle, tan theta in this bigger triangle, tan theta is equal to h by x. So I will be writing down tan theta as h by x. Okay, and obviously tan theta is equal to A by G. So I'll be writing the value of x as h by tan theta and the value of a as g tan theta. So PB will be equal to PA plus h by tan theta into rho into g tan theta. So cancelling again tan theta, PB will be equal to PA plus h rho g. So this is the same result which we have already derived 2 times earlier. So what I am trying to say is the fact that at each equipressure line, the pressure at every point on a single equipressure line is same, and when you are writing down the value of pressure at some point which is below that equipressure line, so you can move in either of the direction. But you should always remember that while writing PA plus x rho g or a, you should always take the distance accordingly, so that when we are moving from A to B, we are moving in vertical downward direction. So the distance should be the distance h, which is between A and B, and the acceleration should be the effective acceleration of the vertical direction only. While moving from C to B, we are moving in x direction. So we should always take the distance between C and B as x and the effective acceleration as a, because the effective acceleration of x-axis is a only. And while moving from D to B, we have to take the length as L and the effective acceleration as under root g square plus a square. So this was the complete analysis of equipressure lines, and in the next video I will be bringing some concept illustration problems to illustrate the pressure at different points in the accelerated liquid. Thank you.